to know what's the position between those two particles. Think of examples like this. We will consider there are two charged particles, one called Q1, another called Q2. And then we know there is a Coulomb interactions between those two charged particles, and however, we don't know how or why they should interact with each other. And then to answer these questions, then the Faraday will introduce a new concept called the field. We use the name called electrostatic field to characterize this field. This is the first concept of field we introduced in our courses, and the field concept is very important in these courses. Let us think about how do we imagine or learn about this field. First of all, we consider there are two charged particles Q1 and Q2, and then surround Q1 there is a stimulated field called electric field. And then if we put the Q2 inside the field, then the field will apply to force to the Q2. Then we can summarize the procedures like this. First of all, we have one charge, then surround the charge, it will stimulate a field called electric field around it. Then we put the second charge called Q2 inside the field. The field will be apply a force to the Q2 called electric force or Coulomb force. Then the relation of the force should obey this Coulomb's law. Then if we talking about this Q2, the Q2 will also stimulate another electric field surround it. And then you will imagine that this new charge will be affect the original field, and then you will got a new field around Q1. And then if you put this Q1 inside the new field, then the new field will apply forces to this Q1. Then we will got these features of the electric field. First of all, the electric field will exert a force on any other charged bodies. That means the electric field will apply a force to the charged particles inside of it. Then the second feature is like this. The electric field would do a work if the charged particles move in it. From these two features, we can learn what exactly the field is. The field is more like a real object in our real world, because from these two features you can learn that the electric field can transfer both the momentum and also the energy. That means the electric field possesses energy and momentum. Then that means you can define a momentum, a mass, an energy associated with this field. Then the field should be has no difference compared to the real object. After we introduce the concept of the field, then the next we want to learn how to describe the field. We introduce the concept so-called intensity of the field. Let us consider like this. First, we think there is a charged particle called Q, which is source charge, which stimulates the field. And then we put a test charge. When you put the test charge, the field will apply a force to this test charge. And in the meantime, we require the test charge has two conditions. First, the size is very small. The second, the charge is very small. The two considers we required it will bring some advantage. Like first, the charge is very small. That means we can measure the field at each spatial point. The second, the charge is very small means that there's no effect on the original field. Then we can measure the features of the original field. Then the procedure is like this. If we put Q1 in the position of Q, and we measure the forces F1, and we put Q2 at the position of Q, then measure the force of F2. Then we can define a ratio between those two guys, and then we define this quantity as the intensity of the electric field. Then we can go to the definition of the intensity of the electric field. We use E here. E is equals to the electric field per unit charge. Then you can find that the E is a quantity which should be the same unit as the forces of F. That means it is a vector. It can both describe the direction and also the magnitude of the electric field. And then, by introducing the intensity of this electric field, we can calculate for several examples. First, for the simplest example, we can think about the point charge. For the point charge, first we can define the interactions between the source charge and the test charge by using the Coulomb's law. Then you can find the F should be equal to 1/4 pi equals 0 times Q0 divided by R squared. And then by using the definition, you can get this E is like F divided by Q0, which equals to 1/4 pi equals 0 times Q over R squared times R0. R0 is labeled the direction of this force. And also, it will be labeled the direction of the intensity of this field. Second, if we extend our system to a system of pointed charges, that means we can label these charges from Q1 to Qn. And then, if we put in a test charge Q0 in the system, you can calculate the total force applied to Q0 by this principle of superposition. And then you will find that the total force should be equals to sum over all Fi. Fi stands for the Qi and Q0, the interaction between two of these two particles. And by the definition, you will get this electric field intensity, which will be the total F divided by Q0. And then you will find that for a system of pointed charges, the total electric field intensity should be the superposition of all the charged field. That is the superposition principle of the source-state particles. And from the source-state particles, we can also extend this description to the charged object. And then we can use the similar methods of the superposition principle in the Coulomb's law. And we can divide it by these charged particles by dq, and then we can calculate this electric field for all the dq's, and then by using this superposition principle to calculate the whole field by using the summation to the integration. And then you can get this formula to describe charged bodies by using this integration. And then for doing this integration, we will introduce three concepts. One is called linear charge density, another is surface charge density, another the volumes charge density to describe the different objects. See you guys next time.